Alright, people, so we'll start rather continue with wave optics. And in wave optics, in the previous slide, rather in the previous session, we had studied about Huygens principle. We have studied about how light behaves both as a ray as well as a wave. So in ray optics, we are just considering the particle nature of light. In wave optics, we are considering light to be a wave. Now, when we consider only the ray optics, or rather the particle nature of light, we have a different group of scientists. Let's say we have Newton, we have Einstein, then we have Planck. All of these people basically support the particle nature of light. And there are a lot of phenomena which can only be explained by particle nature of light. For example, refraction, reflection, which of course we can explain also with wave theory. But then there is photoelectric effect, in which we have a ray of light incident on a metal surface of a certain frequency. Beyond that frequency, which is also known as threshold frequency, there will be emission of electrons. So obviously, light has to be made with particles which were assumed to be photons, and these photons are striking and making the electrons move out. So that basically confirms the particle nature of light. Here we have the wave nature of light. The wave nature of light basically states that light travels in the form of waves. Light is a part of electromagnetic spectrum. In this particular slide, we are going to see how it is a part, how the visible light is a part of the electromagnetic spectrum. So we will quickly see as to what we had studied earlier. We will do a recap on the earlier segments that we have studied about how Huygens principle works or how new wave fronts are basically calculated. So this will be a general discussion, and we will also recap what we have covered. Okay, so in Huygens principle, we had seen that all points on the circle will oscillate with the same phase. Now, as an example, what we took here, since we cannot see light in the form of waves, so whatever we can see in the form of waves, we have considered that as an example. So we have seen how when we drop a stone in water, ripples or waves are formed. Now, if we happen to connect all those waves which are vibrating in the same frequency at the same time, we will basically get a wavefront. So, connecting all these will get a wavefront. The next wave connecting all these will get a wavefront. The next wave connecting all these will get a wavefront. All points in the circle will oscillate with the same phase. So, circular wavefront. This actually will give us a circular wavefront. So all the points, any distance x from the source, oscillate with the same phase. So all these points which are at any distance x from the source will all oscillate in the same phase. So all points oscillating with the same phase form a circular locus as shown, and this is basically a 2D version. So wavefront is what? Wavefront is a locus, which means location of all points of a medium at a particular medium which are vibrating in the same phase at a given instant. Of course, vibration of water particles cannot be compared to vibration that is caused by an electromagnetic spectrum or light waves. But here we are just trying to understand how a wavefront is created. So when we happen to drop a stone in a stagnant water, or let's say pond or lake, what will happen is ripples will be formed. So there will be oscillations which will happen. These oscillations obviously will have a up and down movement. So these oscillations. So all points oscillating with the same phase form a circular locus as shown, because this is the wave. Okay. So wavefront is a locus of all points of a medium which are vibrating in the same phase at a given instant. So they are all vibrating in the same phase at a particular given instant. Okay. This is basically giving us a wavefront. Now, when we happen to talk about a circular wavefront, or let's say a point source of light, what you will see is that from a point source of light, obviously the waves will be like this, okay? And as and when they go very far, this becomes what? Almost a straight line. Now, what will be the radius? Obviously, the radius will become infinity. So, from when we receive light from very far off or distant sources, let's say sun, the wavefront is basically perpendicular. So, a point source forms spherical wavefront. At large distances from the source, the radius of the wavefront becomes very large, infinity, and hence wavefront can be assumed to be a plane wavefront. So, from spherical, it has actually turned into a plane wavefront. The thing that we have to keep in mind is that ray and wave fronts are always perpendicular to each other. No matter if they are circular, no matter if they are basically plane wave fronts, so they are always perpendicular to each other. So a ray and a wave front, a ray and a wave front will always be perpendicular to each other. A ray and a wave front will always be perpendicular to each other. Okay. All right. Let's move ahead. So what do we have? We have types of wavefronts. Source, let's say, is at infinity. There are parallel rays are formed when the source is at infinity. Thus, it produces a plane wavefront. So, when a source is at infinity, we can say that the radius has become infinite. So, obviously, it will create a plane wavefront. These are the rays, and all these will be basically, so it's like this. The wavefront is like this, and these are the rays. So, the wavefront and the rays will be perpendicular to each other. When we have a light source, let's say like a tube light, so this will basically create cylindrical wavefronts. So when we have a linear source, when the source is linear, cylindrical wavefronts are created. When the source is at infinity, the type of wavefront that we get is basically a plane wavefront. The type of wavefront that we get is a plane wavefront. Okay. All right. So Huygens principle states what? That every point on the wavefront acts as a point source called secondary wave. So this is basically the wavefront, new wavefront that we have got. So there are many wavefronts. So this is the new wavefront. Now on this new wavefront, all points will actually behave as secondary wavelets, sources of secondary wavelets. So these are secondary wavelets. Now when we happen to draw a common tangent, now what will be the radius of these? This will be v into t, which is velocity of light in the medium into time. Okay, so these will form secondary wavelets. So every point on the wavefront acts as a point source called secondary wave source and generates secondary wavelets. So these are basically generating what? These are generating secondary wavelets. So these are basically generating secondary wavelets. Okay. So the common tangent to the secondary wavelets is the forward direction gives the secondary wavefront. So this is the common tangent, and this basically gives what? The secondary wavefront. The common tangent to the secondary wavelets in the forward direction gives the secondary wavefront. So this is basically the common tangent. It is going to give us what? The secondary wavefront. Okay. Now we are going to prove the laws of reflection and refraction by using Huygens principle. Uh, by geometric optics, we have already proved this. Okay, so now we will talk about the reflection of light to be proved by Huygens principles. So let the light from infinity. So let's say we are considering light coming from infinity and reaching a plane mirror, reaching a plane mirror. So whenever we have a light coming from infinity, it will always be plane wavefront. Plane wavefront. We just now covered this. So this will be a plane wavefront. So let's say this is a plane wavefront and light is incident like this. Okay. So in an inverted way, it is incident like this. Okay. So it is a little tilted. So let's say this is PA and this is QC, which are both part of the same light incident on this plane mirror. Now, when the ray from P reaches A, the ray from Q has actually just reached B. So understand, P and Q are a part of the same wavefront. Wavefront again, what will be the wavefront? Ray of light and wavefront are perpendicular to each other. So of this incident, right, this will be perpendicular. This will be perpendicular. By the time P has reached A, Q has just reached B. Now understand this. After coming to this reflecting surface, from A the light will be reflected. However, B has yet to reach C. So now we are going to consider these distances. Okay. So covering this distance BC, let's say from point B, the wavelets emerge and they reach at point C in time t. Let's say in the medium, which is just one medium here. In the medium, the speed of light is v. We know that the distance covered is speed into time. So what will be this distance covered? V into t. This will be the distance covered. So BC distance will be Vt. Now let's talk about the wave which has reached A. Now obviously from A it will get reflected. Now how will it get reflected? Again it will become a source creating secondary wavelets. Now, how to get the new wavefront or the reflected wavefront? So, in the same time Vt, we take radius, but for construction. Okay, we take radius to be Vt. We draw an arc, keeping the center of the compass at A. We draw an arc, and this arc has a radius Vt. From point C, we draw a tangent. The moment we draw a tangent, this tangent will have a length of Vt. This already has a length of Vt. Okay, this will have a length of Vt. So understand, radius and tangent at point are perpendicular to each other, and we also know that ray and wavefront are also perpendicular to each other. Radius and tangent perpendicular to each other, and ray, and obviously this will become the wavefront. So this blue line that you see becomes the reflected wavefront. Now let us consider some angles. Okay, so this is the normal, this is the incident ray, PA. So obviously this will become the angle of incidence. Now this is basically the ray and this is the wavefront, incident wavefront. So obviously between the ray and the incident wavefront, the angle is going to be 90 degrees. So how much would this angle be? This angle will be 90 minus I, right? This entire angle is 90, out of which the normal creates an angle of incidence. So obviously this angle will be 90 minus I. Now come to this one, NAC. Angle NAC is how much? 90. If angle NAC is 90, obviously this angle will become I, because this is any which way is 90 minus I. 90 minus I plus I will give you 90. So this angle becomes I. So this is basically deriving, if this angle happens to be I, this angle will be I. Now let's come to R. Here R is the angle of reflection. The normal, the ray of light reflected makes an angle R. Okay. Now this is basically what? 90 degrees. If this is 90 degrees, obviously the remaining portion will be what? 90 minus R. Understand this. This is 90, out of which this is R. So this will be 90 minus R. Now take this triangle. In this triangle, the ray and the wavefront are perpendicular to each other. So that is basically making an angle of 90 degree. This is 90 minus R. This is 90. This is 90 minus R. So obviously this will be R. Okay. So R plus 90 minus R plus, let's say, X is equal to 180. So this gives you what? 90 plus X is equal to 180. So therefore X is equal to 90 degrees. Okay. So that's the reason X has to be R. This X, sorry. So here it will be, let's say this angle is X plus 90 plus this angle is how much? 90 minus R plus 90 minus R. This is equal to 180. Sum of three angles of a triangle is equal to 180. This gets cancelled. So X we have as R. So this angle becomes R. Okay. So now understand these two triangles. Very simple to understand. AE is VT, BC is VT. This is 90, this is 90, and this is common. So in triangles AEC and ABC, AC is common side. This is right angle, and this distance AE is equal to BC, which is VT. So we have by right angle hypotenuse side these two triangles as congruent. If these two triangles are congruent, obviously angle I will be equal to angle R. That's how we prove the angle of reflection. So if the velocity of light in the medium is V and the time elapsed for a point on wavefront to go from point B to point C is T, then BC is equal to obviously VT. So let A end of the wavefront is already touching the reflecting surface, when B end is VT distance away from the reflecting surface. Thus point A will act as a source of secondary wavelets, and in time T it will generate secondary wavelets of VT, and the wavefront at this time will be C. The wavefront C is the reflected wavefront at time T. Okay, so here we have 90 minus I. So these are basically the calculation part here, and we have understood this will be basically what? This is basically the congruency part. Here in triangle this AE will be VT and this will be VT. So if we happen to prove this, this will be I is equal to R. So that basically proves the law of reflection. Now we come to refraction. So what happens in refraction? The light rays basically travel from a rarer to a denser medium, and as soon as they do that, their velocity changes, their wavelength changes, however their frequency remains the same. And Snell's law of refraction states that refractive index of second medium with respect to first is mu2 by mu1 is equal to sine I upon sine R is equal to velocity of light in medium 1 upon velocity of light in medium 2. If we are able to prove this by wave theory, then we are actually proving Snell's law of refraction by wave theory. So let us again take a ray, incident ray, which is coming like this. So this is basically PA and this is ray. By the time the ray has reached A, it will be traveling a distance within the medium. Here it will be traveling a distance in the observed medium. So here it will be time t. So this one will be how much? V1t. Let's say V1 is the velocity of light in this medium. This is how much? V2t. Now how will we get V2t? Now in time t, the ray or rather the wave which was at B, it has covered this distance C. So this will be V1t, the distance covered by the wave at B with velocity V1 in medium 1 during time t will be V1t. At the same time, that is at time t, the distance covered by the wave which has reached A, since it has reached a transparent medium now, light is going to travel, but its velocity has changed. So in the same time t, the distance covered will be speed light speed of light in medium 2, that is v2 into t. So this will be t. Okay. Now if we happen to draw an arc taking radius as v2t, now here the waves are emerging like this. So we take a radius v2t and we draw an arc, and from this we draw a tangent. The moment we draw a tangent, what will happen? This radius AE will be perpendicular to the tangent drawn. Radius and tangent at point of contact are perpendicular to each other, and this is basically the wavefront. Wavefront is the ray. This is basically the refracted ray. Refracted ray, and obviously since this is perpendicular, so this becomes the new refracted wavefront. So here we have a refracted wavefront. So this will be what? This is the same medium, light traveling in the same time. This is the second medium, light traveling in the same time. This is the refracted wavefront. So if you look at it, this EC will be the refracted wavefront. AB still happens to be the incident wavefront. Now let's look at these two triangles. Again, this angle is I. So since this is perpendicular, so this angle will be 90 minus I. This angle will be 90 minus I. If this happens to be 90 minus I, people, okay, so obviously this will be how much? This is 90, so this will become I. Okay, now let's look at this triangle. Here, this is basically R, that is the angle of refraction. If this angle happens to be R, this is 90. This is 90, this is R. So how much will this angle be? This angle will be 90 minus R. This is 90. Normal is perpendicular, so this is R out of this, and this is this angle NAC. This is 90, so this is 90, this is R, so this will be 90 minus R. So 90 plus 90 minus R, again the same thing, 90 plus 90 minus R. Let's say if we happen to assume this angle to be X, so plus X will be equal to 180. 180, 180 gets cancelled, so X is equal to R. So what we are getting here is, if this is the angle of refraction, then this happens to be R. If this is the angle of incidence, then this happens to be I. Now, just hypothetically take sine I. So sine I will be what? Perpendicular upon hypotenuse. That's AB upon AC. So that will be V1T upon AC. And what will be sine R? Sine R will be perpendicular upon hypotenuse. That is AE by AC. That is how much? V2T by AC. So sine I by sine R is equal to V1T by AC upon V2T by AC. So this AC gets cancelled, T and T gets cancelled. Sin I by sin R, that will be equal to V1 by V2. Now we already have V1 by V2. We know that the refractive index is inversely proportional to the speed of light. So we can write this as mu2 by mu1. And this is nothing but the law of refraction. So this is nothing but the law of refraction. Okay. So this will be V1 by V2, sin I by sin R will be equal to V1 by V2. V1 by V2, mu2 by mu1, that is Snell's law of refraction. Okay, let's look at the electromagnetic spectrum. We know that a very small portion of the entire electromagnetic spectrum is actually visible light. So let's look at this. So as and when we see in electromagnetic spectrum, we have radio waves, then we have microwaves, we have infrared, we have ultraviolet, we have X-ray, we have gamma, and so on and so forth. You see this wavelength decreasing. So from 360 nanometers to 780 nanometers, that will basically form what? That will form the 360 to 780 nanometers. This is going to form what? This is going to 360 to 780 nanometers. 360 to 780 nanometers. This is going to form the visible wavelength. This is going to form the visible wavelength, or rather the light that we see. Okay. Now, there are some phenomena which can only and only be explained by wave optics. For example, diffraction is a phenomena, interference is a phenomena, polarization is a phenomena. These are phenomena which cannot at all be explained by geometrical optics or ray optics. So what is diffraction? Diffraction is nothing but when you have an aperture or a block which is very tiny, or which is very tiny in magnitude, so tiny that its dimensions can actually be compared to the wavelength of light. So in that case, the whole dimensions are basically greater than the wavelength of light. So when light passes through a hole having dimensions greater than the wavelength of light, the light travels in straight lines without changing direction. So this will travel in straight line without changing direction. So this is basically the straight line without changing direction. The straight line motion of light is known as rectilinear propagation of light. Okay. So here the apertures, let's say there is a window and there is a sunshine. The sun is shining, you will see straight lines. Okay. But when this window aperture becomes very small, when the whole dimension is comparable to the wavelength of light. Again, we have seen what is the wavelength of light, 360 nanometers or 780 nanometers. Okay. So when light passes through a hole having dimensions of the order of wavelength of light, the light doesn't follow the straight line path. It doesn't follow the straight line path. What will happen here is this aperture will actually, this should be the case as per geometric optics, but you will see that there is bending of light. This is basically bending of light, and this will happen only in diffraction. This will happen, this will happen only at this process is known as diffraction, and this can only be explained by wave optics. This can only be explained by wave optics. So describe this behavior of light, we need to consider the wave nature of light. That is, from the source, the light emits spherical waves. So light is basically emitting spherical waves as shown in the figure. This part of optics is known as wave optics. So we'll consider this as wave optics. Okay, so let's take an example here that we have some water out here. We have dropped a small stone and there's a can out here, a Coca-Cola can or whatever. So you will see the aluminum can tossing up and down. Why? Because waves are formed. Let's say the amplitude of this oscillation is 4 centimeter. It goes 4 centimeter up, 4 centimeter down. Okay, suppose a Coke can is placed on the surface of still water and a small stone is dropped on the right side of the can. Because of this, circular waves are generated on the water surface. Again, please do not consider water waves and light waves to be the same. They are different. But since we cannot see light waves or understand their phenomena visibly, we are taking an example of what we can see visibly. Okay. So since the wave is nothing but a collection of simple harmonic motions, it has a crest and it has a trough. Okay, so it has a crest. It will. So this is basically the crest and this is the trough. So it will have a crest and it will have a trough. The crest will be 4 centimeter and the trough will be 4 centimeter. Okay. If a stone of slightly heavier than previous one is dropped on the left side of the can, then the can is raised up by 8 centimeter and this is what will be generated, 8 centimeter up and 8 centimeter down. Okay. So now if both the stones that were dropped individually in water in the previous cases are now dropped simultaneously on either side of the can and shown in the figure, consequently the wave generated by the stones will reach the location of the can at the same time and the resultant effect is expected to be absorbed. So now they will see a resultant effect. Now what will happen? This is coming from 4 centimeter. This is coming with 8 centimeter. So what you will see is again 12 centimeter. But in case they are meeting like this, so let's say this is 8 centimeter and this is 4 centimeter, then the resultant will be just 4 centimeter. In case the crest of one is meeting with the trough of the other, then the resultant wave amplitude will be 4 centimeter. And in case both the crests are meeting together or both the troughs are meeting together, then the resultant amplitude is going to be 12 centimeter. Okay, this is the same thing that is applied in waves. So if we have a wave with amplitude y1 and if we have a wave with amplitude y2, when they combine together, they will generate a net amplitude of y1 plus y2. So that's the superposition principle. So when two or more waves cross at a point, the displacement at that point is equal to the vector sum of the displacement of the individual waves. So when two or more waves are crossing at one point, the displacement of that particular point will be the sum of the amplitudes of both the waves. So vector sum means, now what do we mean by vector sum? So let's say this is going, this amplitude is towards this and this is meeting with the trough of the other. So what will be the vector sum here? This will be y1 minus y. This will be the vector sum. The vector sum here in this case will be y1 minus y2. In case both the crest or both the troughs are meeting simultaneously, then it will be y1 plus y2. In case the crest of one meets with the trough of other, then the resultant amplitude will be y1 minus y2. Okay. Alright, so superposition principle, if two wave pulses, one having an amplitude of 1 unit and the other having an amplitude of 0.75 unit are moving towards each other from opposite side with same velocity, they will superimpose at same point and the amplitude of the resultant wave will be how much? 1.75 units. So this will be the amplitude, 1.75 units. After the superposition, the shape of the wave pulses remains unaffected. So after the superposition, it will become one wave. If two wave pulses, one having an amplitude of 0, so this is the vector sum, 0.5 unit and the other having are moving towards each other from opposite side with the same velocity, At the instant of superposition, the amplitude will be zero. It means that there will be zero displacement of the particle. One is coming like this and the other one is coming like this. So this will be the one is basically crest and the other one is trunk. So there will be a zero displacement. Therefore, the pulses cancel each other at the instant of superposition, and after the superposition, the shape of the wave pulses remain unaffected. So after superposition, the shape of the wave pulses will remain unaffected. So this was a small part about Huygens principle. We have already seen how to construct wavefronts, what are spherical wavefronts, what are cylindrical wavefronts, what are plane wavefronts. We have already seen that how to prove reflection of light and refraction of light by Huygens principle, and we have already seen what is electromagnetic spectrum and how is light a part of it, and what is the superimposition principle for waves when they are basically meeting, so that their crest and their individual troughs are meeting, so their amplitude will be magnified and it will be a vector sum. When they are meeting in such a way such that the crest of one meets with the trough of the other, they will cancel each other. So that was about it. We will cover more in the next slide, people. Stay tuned.